Okay, good morning, class. Let's go ahead and get started. First thing is I have a couple of announcements. This is an early drop deadline class, so whoa, getting lots of feedback up there. Okay, this is an early drop deadline class. The deadline is tomorrow, so if you are planning on dropping, then that is the deadline. Oh, now I have no microphone. Better? You guys hear me in the back okay? Yeah, okay, great. So, thank you. Tomorrow is the deadline, the early drop deadline. So if you have joined us and you are planning on leaving the class, then thanks for coming. We still have quite a long wait list, so I think your fellow students will be very eager to see you go. And that also means there are a lot of new people coming in the class this week, especially this lecture. All the past lectures, much to my horror, are webcast, so you can get to those through bSpace. Also, we have the course information sheet, which you need to read very carefully. That's on bSpace as well. And you need to sign on to our homework system, Wiley Plus. So all that information is on the bSpace course site, which you should be able to get on pretty quickly. And if you can't get onto it within 24 hours after registering, after getting in the class, then send me an email and we'll check and see what's going on with your registration. Sorry? Yes. I think, so the question was if you've already registered for Wiley Plus and you want to drop the class, do you lose money? I think so. That's between you and Wiley Plus, so I don't have any say in that. So I do not know the answer to that, but I don't think they will give you, they will reimburse you for that. So, yeah, back there. I do not know the answer to that question either. I certainly could not, I don't want to know. So you guys should talk to each other. Maybe that's what the forums are for. I won't pay attention to that forum post. Okay, let's go ahead and get started then. So today we are going to be talking about Newton's third law. Which is commonly known as the law of action and reaction. Okay, Newton's third law is very easy to say, but conceptually it seems to give students the hardest time. So let's go over that a little bit. Newton's third law just says that forces never appear alone. In nature, they always appear in action-reaction pairs. Okay, if you'd like to, you can think of this as the karma of physics, which is if you push, you get pushed back. There is no force that appears alone. So if you've got two objects, object 1 and object 2, these can be balls or people, cars, anything you want to think about, planets. Then if object 1 starts exerting some force on the second object, ringers off please, and the second object, object 2, is going to exert the exact same force back on the first object, equal in magnitude, so the forces have the same strength, the same push, but directed in opposite directions. They never the forces never appear alone in nature. They always appear in action and reaction pairs. Okay, so the problem that I think people have with this is a really good question, which is why don't these forces just balance out? If for every force there is a reaction force in the opposite direction, you think that they would just cancel out and we wouldn't get any motion at all. The answer to that is the question you always have to ask yourself when you are dealing with action-reaction pairs is that the forces do not act on the same object. Okay, so the action-reaction pairs always work on different objects. Okay, so in this example I just gave you, this object 1 is providing an action on object 2, providing a push on object 2 that wants to accelerate object 2 over to the right. Okay? The reaction to that action, so the reaction of the action-reaction pair, is that object 2 pushes back on object 1 with the same force in the opposite direction. But this force is accelerating object 2 up to the right, and this reaction force is accelerating object 1. They're not working on the same object. Okay? So that is the hardest part of the third law, and if you always keep that in mind when you're looking at action-reaction pairs, then you will probably have no problem understanding this basic concept. Let's do a counterexample to that. Another one of my exciting demos. This block sitting on this table. Okay. This block we know is being pulled down by the gravitational force of the Earth, so its weight is pulling it down, and the table is providing a force which is pushing it back upwards. Okay. So it's got the force down, the force up. Let's draw a picture of that. So here is our block. It's got its weight acting downwards. It's got the table pushing upwards on it. And we can see that block is not moving. So we know that these forces are balanced, right? They are equal in magnitude and opposite in direction. So these two forces are balanced together. Okay. They are equal in magnitude, opposite in direction, so you might think that they are an action-reaction pair, okay? But they are not an action-reaction pair. And the reason they are not an action-reaction pair is because both of these forces are acting on the block. Okay? So you can see immediately that they can't be an action-reaction pair. They're balanced with each other. Absolutely, that block isn't moving, but they're not an action-reaction pair. So let's pull out the real action-reaction pairs out of here so we get a better feel for what those are. Okay, for every force, there is the reaction force. So let's look at the first one, which is just the weight. So this is the action-reaction pair number 1. Okay, that is the weight of the block. Which is pulling downwards. That is a force that is provided by the Earth, the gravitational pull of the Earth. So the reaction force to that action force has got to be the block acting on the Earth, which it is. That block is pulling back up on the Earth. Okay, we usually don't think about this when we think about gravity, but let's point that out. So gravity is pulling this block downwards. Okay? This block is exerting the reaction force on the Earth, which is this block has a gravitational force, which is pulling upwards, back upwards on the Earth itself. Okay? So this block, when it's sitting here, is actually pulling upwards on the Earth. Okay? The problem, I mean, not the problem, the difference in the dynamics is, of course, this block is really light, right? Very low mass compared to the Earth itself. So the force that this block is providing doesn't accelerate the Earth very much. Okay? Certainly much too small for us to measure. Okay, so the Earth looks like it's not moving, but in reality, it's accelerating because this block is sitting here. Okay? It's the action-reaction pair of those. Okay, the second one is probably obvious now that we've got that first one pulled out. It is the force of the table holding up the block, which has the reaction force of the block pushing down on the table. Okay. So there are two action-reaction pairs going on in this situation. Okay? There's the weight of the block, which is a reaction pair with the block's force on the Earth, back on the Earth. And there is the force of the table holding up the block, which is a reaction pair with the block pushing down on the table. Right? Okay, yes?
Are you saying that, I thought you said that the block sitting on the table wasn't an action reaction, but now I feel like that's what you're saying.
No, I'm saying that it's a more complicated situation. So let me draw it for you again, okay? So we've got, when we first drew the block here, okay, the block is sitting on the table. If we look at the forces acting on the block, right? On the block, we have the weight going down, and we have the table pushing up. Okay. But both of those forces are acting on the block, so they can't be an action-reaction pair. The other things that we're missing here, okay, are that there's the weight of the block pushing down on the Earth, but the Earth is being pulled up by the force, the gravitational force of the block. So this is the force on the Earth itself. So this is the pull of the block, okay, on the Earth. And then there's also, so the table is pushing up on the block, but the block is also pushing back down on the table, right? The block is absolutely acting on the table. There's a force of the block on the table, right? Pushing downwards on it. Okay? Two forces, there are two forces acting on the block, right? There is the table pushing up, and then it's the weight of the block pushing downwards. Okay? Those are the two forces acting on the block itself. Okay? Then there's the other forces are acting, the block pushes down, it's actually pushing on the table. So the action-reaction pair there is let's just draw the action-reaction pair. So here's the block, and here's the table. So the action is that the block is pushing down on the table, and the reaction is the table is pushing back on the block, right? Gravity, weight, yeah, weight is gravity. Weight is the gravity of the block. So then the other action-reaction pair is independent of the table. It's that the block has its weight acting downwards, and then there's the counter force of the Earth being pulled up by the block. Okay, yes? So the question is, she thought that gravity pulls down on the block, right? So you're asking why does the block pull back up on the Earth? So this comes from Newton's third law. Okay? Remember, the weight is a force, the weight of this block. This is the gravitational pull of the block being attracted down to the Earth. Okay? So Newton's third law tells us that that force has to have a reaction force, and that reaction force is on whatever object is exerting the force on this, which is the Earth. Okay? So gravity is a force that acts between all masses. So any two masses that we have will be gravitationally attracted to each other. It's not just an attraction from us to Earth. Okay? There is a gravitational force between these two blocks that are trying to pull them together. Okay? It's just their mass is so small that it's completely insignificant compared to any forces around us. Okay? Any two objects attract each other. This one's exerting a gravitational force on this block, and the reaction is this block is exerting a gravitational force on this block. The difference with the Earth is just the Earth is so massive that it doesn't accelerate at all from that gravitational force, or it's a very small acceleration. Yeah, last question on this. Okay, so the question is, what is the difference between the weight and the block pushing down on the table? Okay, that is also a very good question. In fact, let me just go back here. Well, actually, let me go over here and show you this. Okay, so the weight is completely the reaction between the block and the Earth. So it's the forces between the block and the Earth. That always is there, regardless of whether the table's there or not, right? So the Earth is always pulling down on the block, and the block is pulling up on the Earth. Okay. So if you put a table there, right? So imagine we got the block here without the table underneath it. Okay. It's being pulled down. I have to hold it up. Okay. And I let it drop, it lands on the table, right? So then, since it's not accelerating, there has to be a balanced force, and the balanced force is the table pushing back up on the block. It's the support force. It's also called normal force. We're actually going to talk about it more in this lecture. So we'll come back to that in a few minutes. Hopefully I'll make it clear. Okay? See, I told you action-reaction was the most confusing of Newton's laws. Oh, in fact, you anticipated my next topic, exactly, which is support forces and normal forces. Okay, so let's talk a little bit more about exactly what we were just talking about, which is the force of the table pushing back up on this block and holding it up. Okay? We have two names for that. We can call it, somebody else has blocks up there too. We can call it the support force, or what we normally call this in physics is the normal force. Okay, so let's go back and do our own individual experiments again, which is your hand on your desk. Okay. You are going to be providing the force downwards, so you're going to be pushing down on your desk, and you can feel the support force of the desk pushing back on you. Right? This force, this resistance of the desk is called the normal force, or the support force. Okay? And there's two things I want you to think about when you're doing this. First is that the normal force is always balancing the force that you're pushing down with. Okay? So that means the magnitude of the normal force, or the support force, is going to increase when you push harder. Okay? That's pretty intuitive, right? You push down harder on the desk, it's going to push back harder on you. Don't break any of these desks, please. We're poor in California these days. Okay, so you push down and it pushes back on you. The harder you push, the harder it pushes back. Okay? So the support force is not just a constant number. It is whatever force it needs to be to counter the force that you're pushing down with. Okay? And the second thing, which is obvious, of course, is that the support force is directed in the opposite direction from where you're pushing. Okay? You're pushing down on the desk, and the support force is pushing upwards. Okay? It's an action-reaction repair, right? So I'm pushing down on the desk, and the desk is pushing back up on me. Okay? Equal and opposite in magnitude. Okay, so it's this reaction force is what makes solid solid. Okay? If we didn't have that reaction force, then when we push down, our hand would just go right through the desk. Okay? At the microscopic level, this is due to electromagnetic forces. Forget I said that. We'll come back to that later in this semester. But there are microscopic reactions that are going on that keeps us from, our hand just going right through the material of this desk. Okay? From our standpoint right now, we just need to know that this is a solid, so it's pushing back on us with an equal and opposite force from what we're pushing down. Okay, so normal, when we call this the normal force, we mean that in the mathematical sense, not in the social sense. Okay? We don't have abnormal forces in physics. Normal means perpendicular mathematically. In this case, it's perpendicular to the surface. Okay, so let's draw a picture of that just to be clear. So here is our block or whatever object we're looking at. Here is the surface it's sitting on. It's providing its support. The normal force is always directed perpendicular to that surface. Okay? So it's always forming a right angle in direction with that surface that's providing the support. Okay? So if we were doing this on an incline like this, so let's say that's a ramp. So we take that same object on that surface, and we're just going to lift it up. Okay, so here's our block, and here is our surface. Right now, the normal force provided from this surface onto the object is straight upwards. Okay. Now we're going to tilt that up like this. You can see the surface is now at an angle, which means that the normal force has changed its direction as well. So if we're on a surface like this, and here's our object, okay, so this is our surface. If the surface gets inclined, the normal force gets inclined as well. So the normal force, the support force, is always directed perpendicular to that surface. If there is any force between the surface that is not perpendicular to that, okay, so along the surface, so intuitively we know if we were to take this object and tilt the surface up like that, it would want to slide. Should want to slide. What's keeping it from sliding? Friction, that's right. So if there's any component of force along there, the surface, it's provided by friction between the two. Okay? So the normal force is always perpendicular to the surface. Friction is always parallel. Okay, so at this point, we can start talking a little bit about ramps, okay, which are a very useful tool. So ramps are just a tool that takes advantage of this normal force always being directed perpendicular to the surface. Okay. Ramps. So ramps basically take advantage of that normal force in order to allow us to lift heavy objects. Okay? And let's talk a little bit about how that works. Okay, so drawing the same picture over here, once again, I swear I'm not going to draw objects on flat surfaces the entire semester. There is our object and there is our surface. Okay? The object in this sense, if it's just sitting on there, the object is being acted on by balanced forces. So that means there's no acceleration. Okay, so that is just the weight of that object, and that weight is always directed downwards, okay? Always directed towards the earth. Okay? And then there is the normal force, or the support force, which is always perpendicular to the surface. Okay, in this case, those two forces are perfectly balanced. And because they're balanced, there's no acceleration, and the object doesn't want to move. Okay? Now, let's take that object on the surface, and let's tilt the surface and look at the forces. So we're going to tilt the surface, which means we're just turning it into a ramp. Here's our surface once again. Here is our object, our heavy object that we are trying to lift up that ramp. Okay. Now let's draw the forces on that object again. So remember, there is the weight, and the weight is always directed straight downwards. Okay. And there's the support force, or the normal force, of the surface holding up that block or that object. Okay. So that's the normal force acting in that direction. Now, a key thing to notice here is that these two forces, when we tilt that ramp, are no longer balanced. Okay. And they're no longer balanced because they are not directed in opposite directions of each other. Okay? The weight is pushing downwards, and the normal force is pushing up at an angle. Okay? So when we put those two forces together on that object, they can't balance each other out because they're not directed in the same direction. Okay? Independent of the magnitudes of them, okay, they're never going to cancel each other out. They're always going to be unbalanced. Okay? The fact that they're unbalanced means that, intuitively, if you put an object on a tilted surface like this, it's going to accelerate, right? Unbalanced forces means that we have acceleration. Okay? There's two ways to keep this object from sliding. One is to rely on friction. So if we don't tilt it up too much, then the frictional force between the block and the surface is going to provide the balancing force on this and keep it from moving. Okay? But that's only true if we make the surface kind of rough, right? And the block kind of rough. If we make these really smooth and totally get rid of friction, then there will never be a balancing force provided by the friction, and this thing will always accelerate. Right? That might sound like a bad thing, but it could be a good thing too if you're trying to lift that heavy object up the ramp. Okay? So, so if we make the surface smooth, or if we make the ramp smooth, there is no friction. In which case, we have to provide the balancing force. Okay. In order to keep that block from sliding down, there has to be some smaller force that is directed up that ramp that is balancing those forces. Okay, intuitively, we know that these, so when it's flat like this, the forces, the weight is downwards, the normal force is upwards, they are balanced. Okay? As we tilt this up, okay, the angle between them becomes greater and greater, so the difference between the normal force, it gets tilted over more and more and more. Okay? The weight always stays in the same direction. So the more tilted it is, okay, the more unbalanced the forces are, which means that this is going to accelerate faster, right? The higher it is, the more unbalanced the forces are. But that also means that we have to provide more force in order to push back on it, to balance it. Okay, so the higher this is tilted, the more unbalanced those two forces are, and the more support we need to provide for the balancing force. Okay, so the extreme case of that is if we take this and tilt that surface completely right angles, right? So this is a really tilted ramp. It's not a very practical ramp, okay? But the extreme example of that is if we tilt it all the way up to 90 degrees, okay? Then they're completely unbalanced, right? Because the normal force would be directed out this way, gravitational force is down that way, in which case we have to provide the complete balancing force, right, to hold this block up, okay? So 0 balancing force needed by us because they perfectly balance each other, okay? And then it increases as it goes up and up and up to the point where we have to provide the entire weight balancing force for the weight. Right? In this case, the normal force goes to 0. There's no push of this block against that surface because there's no weight for it to counter. Okay, so this leads to our first example of mechanical advantage, which is using these laws to do remarkable things. Okay, it's this trick that lets us do things like, well, bring heavy boxes up to our dorm rooms, I guess, but also to build things like the pyramids. Okay. Let's say we got this table here, right? We want to take some block and move it up there on top of that table. Okay? So there's two ways of doing that. I do this completely backwards. Let me turn it around this way. So here's our block. Okay. We want to lift that block up onto the surface of the table. Okay? There's two ways we can do that. One is we can just provide a force, okay, upwards, lift it up. Okay, that force has to counter the weight. This is U, pushing upwards. So you have to completely balance that weight of that object and just move it up and set it on top of the table. Okay. The other option is the ramp, which is taking advantage of the mechanical, using the mechanical advantage. Okay. In this case, we can lift the same object up on that table, okay, but we're taking advantage of the normal force to balance most of the weight. Okay. And in order for us to move that block up the table, we only have to provide a very small force. Just to balance out that little bit of difference between the normal force and the weight of the object by putting it on the ramp. Okay? So of course, the steeper that ramp is, so the shorter that ramp is, the more force we have to provide. Okay? So ramps are great if they're a very shallow angle. They're a very steep angle, not so helpful. Okay? Okay, are there any questions on ramps? Yes? So the question is, 45 degrees the ideal angle for pulling up objects on a ramp? No, absolutely not. So like I was just saying, actually this is a good question for work and energy too, which we're getting to later on the lecture. So, but the 45 degrees is not the magic angle for everything. So so like I was just saying, the steeper the ramp is, so the higher the incline, the more force you need to provide. Okay? So if you're moving things that aren't very heavy, okay, that aren't so massive, then maybe you want to use a little bit steeper ramp because you don't have to provide so much force. If you're pushing 10-ton blocks up to the top of a pyramid, you probably want to use the shallowest ramp you possibly can so that you don't have to provide very much force in order to move it up the ramp. Other questions on the ramp? No. Good class. Okay. In that case, it's quiz time. Yay. Okay, I'm going to need my computer. So I'll give you guys a minute to get out quiz slips. If you're new to the class today and you have no idea what we're doing, talk to one of your neighbors and see if you can get a quiz slip off of them. So this is a very friendly class. I'm sure that you'll find somebody to help you out. Anybody that doesn't have a quiz slip, raise your hand. You guys came very prepared today. I am impressed. Okay. Remember to put your name on those, please, and your student ID. Circle your section number. You guys will have this is a good way for you guys to memorize your student ID. Huh? See, the quizzes are good for many things. Okay, question number 1. Which of the following devices on a car can be used to cause the car to accelerate? A, the gas pedal. B, the brake. C, the steering wheel. D, all of the above. Okay, let's go on to the next question. Question number 2, suppose you're a football player and you kick a ball for a field goal. Ignoring air resistance, the ball's horizontal velocity, I'm going to underline or stress horizontal velocity there. A, changes throughout the path due to gravitational acceleration. B, is maximum at the top of the path. C, remains constant throughout the path. And D, is 0 at the top of the path. Okay, let's pass those to the right and left, and GSIs are going to come up and pick those up. Okay, Wei, I'm done with the computer. Thanks. Okay, hopefully that got some of your wiggles out. We can pick back up. So, we have just gone through Newton's 3 laws. Okay. Woohoo! Yay, okay, give yourself a hand of applause. Newton's 3 laws, you made it. Okay, very often when we are thinking about problems in physics and in the world around us, going back to Newton's basic 3 laws, while they're really important to know, is not necessarily the easiest way to think about all the situations that arise, okay? Especially very complicated situations. And so we have developed a number of concepts that sort of build off of Newton's 3 laws, and which just allow us to look at the interactions of forces in a little different way. And the first one we're going to study is the concept of energy. And work, which is related. Okay, so work and energy are not new concepts, fundamentally different from Newton's laws. They are completely derived from Newton's 3 laws. Okay? It's just a different way of working with them and looking at them. Okay? Energy actually is an amazingly difficult concept to define. Right? We, for our class, we're going to think of energy, or in general, this is how I think about it anyway, is a resource for action. It provides us with an ability to do stuff, interesting stuff. If there's no energy, we wouldn't have any resources for doing things. Okay? Energy is actually a concept that's derived naturally from Newton's laws. And the physics definition, if I gave you the full definition here, would be very unsatisfying. So it's good to think about it, how it's actually applied as a resource for action. But what makes it interesting in the physics definition, and a concept that we need to keep in mind when we're thinking about energy, is that energy is conserved for any system. We'll be talking about, we're just going to introduce the concepts of energy today, and it's going to be a very big part of our whole discussions for the rest of the semester. So this is just our first introduction to it. So by conserved, what we mean is that energy is a finite resource, okay, and that it is neither created nor destroyed. It comes in different forms, and we'll see a lot of examples of energy changing form from one form to another. But the total amount of energy is conserved during those processes, okay? And we'll see a lot of examples of that. Let's just list some types. We're going to see more types, but the first three I want to introduce are, just to get us started on this discussion. The first one is kinetic energy, which is just the energy of motion. Okay. When you push on the gas pedal on your car, you're converting the energy that's in the gas tank, which is chemical energy, by the way, which we will talk about as well. You're converting that chemical energy in the gas tank into the kinetic energy of your car, okay, which is basically you're giving that mass, you and your car, a velocity, and you're transferring the energy into kinetic energy. There is potential energy, which takes a lot of different forms. Okay? We'll be going over a number of those, but whenever we are talking about potential energy, you should be thinking about that in terms of stored energy. Okay? It's just energy that's been stored in some form. And the first example we're going to talk about today is gravitational potential energy. And I would claim that this block has potential energy that is stored in it. Okay? And it's stored because it's sitting in a gravitational field. And how do we get that energy out of it? Exactly, we drop it. Okay? When I dropped it, you could see that it was first gaining kinetic energy, okay, as it fell. And then when it hit, that kinetic energy was transferred to two other forms. Any guess what those forms are? So what did you say? Thermal, that's right. Thermal is the big one. That's where most of the energy went. Where's the other one? Sound, that's right, the sound you're hearing. Okay. The sound is the more noticeable of the two. When I drop that, that's actually a very small amount of the energy. Most of it's going into thermal energy in the block and in the table. Okay. So that's going to, let me put that last one down. Which is thermal. And this is technically wrong, calling thermal energy heat. But we'll come back to that when we get to talking about thermal energy more. But that's the way, that's okay for us to think about that right now. Oh, if you want to feel thermal energy in action, hands rub them together, rub them hard. You'll feel them start heating up. Okay? You are taking the kinetic energy of your hands, transferring it into thermal energy between them. Yay. Okay, so energy is a resource for action. Let's define another term. Work. Okay, work is not energy, but it's very closely related. Work is just the transfer of energy from one object to another through forces. Okay, work is how we transfer energy. It's the amount of energy we transfer. Right? Work by itself is not a quantity like energy is. Okay? Work only happens when you transfer the energy from one object to another. Right? So work is done by forces. I think that's intuitively not too hard to understand. If I push on this block, right, I'm exerting a force on it, and I'm giving it kinetic energy. It's going to slide. So I've transferred energy to that block by applying the force on it. So I've done work on it. Technically, the definition for work is equal to the force we apply on the object multiplied by the distance that force pushes the object. This definition of work derives from Newton's laws, and we're not going to drive it in detail, just try to get a little bit of an intuitive feel for why that's so. Okay. So this definition tells us that when we apply a force onto some object, we only do work on it if that object moves as a result of that force. Okay? So when I push on that block, I am doing work on it because it's moving through a distance. If it doesn't move, then I'm not doing any work on it. There's no energy that's being transferred to that block. Okay? So, for example, if I can push on this wall, okay, I can push on it all day, and I'm applying a force to it, but that wall is not moving. Okay? So that force is not acting through any distance. I'm not doing any work on this wall. I'm not transferring any energy to it. Okay? I might be getting tired, but I'm not transferring any energy to that wall. So I'm mostly just wearing myself out. Okay? Another thing to keep in mind is that work can be positive or negative. So when I push that block, okay, I'm pushing it and the force is acting in the direction that it is moving. I'm doing positive work on that block. I'm transferring energy to it. Now imagine that block is coming back at me, and I'm going to push back on it and slow it down. Okay? So you throw that block at me, and I'm going to put a force on it and stop it. Okay? That block is coming in this direction, and the force is directed in the backwards direction, okay? Which means that I am actually doing negative work on it. I am taking the energy, the kinetic energy, away from it, okay, by applying the force in the backwards direction. So work can be positive or negative. Yes? Friction is a negative force. That is a great question. Sometimes. Let me give you two examples of that. Okay? So, is friction negative? Is a negative force? Does it always do negative work? In this case, friction is absolutely doing negative work, right? I give it kinetic energy. The friction is resisting the direction of motion. It's slowing it down. Another example. 2 blocks stacked on each other, okay? I'm going to push on the bottom one, and I'm going to speed them up. There is friction that is resisting the bottom block. This top block, I'm not pushing on it, right? The top block is only moving because the bottom force is applying friction to it. Okay? If there were no friction between these blocks and I pushed on the bottom one, we know from inertia, right, that this block would just drop. It wouldn't move. The reason that block accelerates is because there's a frictional force between these blocks that's accelerating it. And in that case, the frictional force is working to accelerate it, and it's doing positive work. You have to look at the forces carefully. That's right. That's right. So our intuitive feeling is that friction always does negative work, okay? But that's not always the case. Friction can do positive work. Yes? That is actually not, it is a transfer of energy. So if I'm heating up the wall, just because, you know, I'm hot, and the wall is cooler, I am transferring energy, but that's actually heat flow and not work. It's a separate quantity. It is a transfer. And so that's why I put heat in quotation marks here. We often use thermal energy and heat interchangeably, but it's the same way as work and kinetic energy. So thermal energy is how hot something is, and heat is the transfer of that. So the heat flowing from my hand to the wall is a transfer of energy between the two, which is separate from the mechanical work I'm doing on the wall. Last question on this, yeah?
In the mechanical advantage setup that you have over there, I don't know if force and distance are directly proportional, do you do the same amount of work to lift that weight, that block straight up, and to put it up the ramp?
Ah, that's a great question. So he was asking if we do the same amount of work in both of these cases that we gave earlier, if we lift it straight up or if we go up the ramp. And that's exactly where this lecture is going. So we will get back to that in 1 second. That's a great question. Okay, so to do that, let's talk about, we'll come back to kinetic energy next week and talk about that in more detail. But I think intuitively, it's okay. We know that when something's moving, it's got a speed, it's got a mass, it's got some energy associated with the fact that it's moving. Let's talk about gravitational potential energy. Okay, so gravitational potential energy is the energy that is stored in a block or any object just because it can fall. Okay? So, and this does come back right to the question that was just asked. So I'm going to keep that up there, if I can remember. And let's write down gravitational potential energy. Okay, gravitational potential energy. By potential energy, once again, we should think of this as stored energy. Okay? There are many ways to store energy. Okay? We can store it chemically, we can store it in batteries, which is also chemically, food, which is also chemical. We do a lot of chemical energy storage. But using gravity is another way to store the energy. So potential is stored, and of course gravitational means that it's stored by height or stored by lifting, and it's released by falling. Okay, so we've already seen if we drop an object that we have what we're defining as gravitational potential energy that is converted to kinetic energy as it falls, and then primarily thermal energy, okay, when it comes to a stop. Let's look at the reverse question, which is not falling but lifting. Okay, so let's say we have that block, okay, and we want to store some energy in this block by lifting it up. Okay? So we're going to be lifting it up through some distance. And in the act of lifting it up, we have to apply to it a force to it. Okay? So we have a force that we are applying to it, acting over a distance. So we've done work on that block. Okay? So here's our block. It's got some weight that's acting downwards. We're going to lift that block up. That's supposed to be the same block through some distance or height. Okay? And in order for us to lift that block, right, we have to provide at least the balancing force to move it upwards. So there's our hand. Pushing upwards on it. And in order to lift it up, we have to basically balance the weight, right? So the force that we are lifting up on that block is at least the weight, right, of the block to counter it. Okay? We could push it up with a higher force and it would be accelerating, and in which case we would be giving it kinetic energy as well. But we're just thinking of the case where we're lifting up slowly. Okay? And so we're not really giving it kinetic energy. The slower we do it, the less kinetic energy we give it. We're just transferring potential energy. To lift it slowly means it's not accelerating, which means that we are countering those, we're balancing those forces. So the only force that we're applying on it is the balance force to its weight. Okay? So we've got how much work we're doing. The work we've done is equal to the force of our hand times the distance. Okay, this is our definition of work. Okay? And in this case, the force that our hand is just the balancing force from the weight, so it's just the weight of the object. And the distance that we are moving it is the height. Okay? So when we lift an object in a gravitational field, we have to do amount of work which is equal to the weight of the object times the height that we're lifting it to. So that work is how much energy we are transferring to that block, okay, which means that that's how much gravitational potential energy is stored in the block when we lift it. Okay, so the gravitational potential energy, I'm just going to write it GPE because I'm lazy and I'm running out of room on this board. Okay. That is equal to the weight of an object times its height above the ground. And that is how much energy is stored in the object, and we can get back out of the object by letting it fall. So that is the stored energy. Let's do a couple of examples of that. Here is a surprisingly heavy bowling ball. Okay, so yes, sorry. What units is that expression in? Gravitational potential energy. So we've got a weight times a height, okay? And that turns out to be, there are lots and lots of units for energy. And we will talk about that next week. So at this point, don't worry about it. So we're going to primarily use 2 more everyday units of energy around in this class. So we'll talk a little bit about calories, because that relates to food, and it's a good one for people scales. And we'll also talk about kilowatt hours, which is used a lot when you're talking about energy in terms of gasoline or household usage. So for right now, let's not worry about the units, and we'll get back to that. Okay, so bowling ball. I am going to lift this up a little bit. And when I'm lifting it up, I'm increasing its height. So you can see that it starts off down here. I'm applying a force to it. And I'm raising it up. So it's increased its height, which means I've stored gravitational energy in it. Okay. And so I'm going to let it go. And we're going to reclaim that gravitational energy. And it's going to be converted to kinetic energy. Okay, so we let it go, and it swings back and forth, right? It comes up here to the back to me, okay? And at this point, it's stopped, right? And then it turns back around. But when it comes up to this point, it's stopped, which means its kinetic energy is 0. Okay? In which case, it's got the full gravitational potential energy that I initially gave it. Okay? Now let's follow this through as it's swinging down. Okay? At the bottom, it's back to its original height, right, where it was sitting before I gave it any energy. At that point, we would say its gravitational potential energy was 0, or at least it was minimal. But in that case, it's swinging the highest, it's fastest, right, at that bottom point. And that's because it has converted the gravitational potential energy into kinetic energy as it falls. Okay? And then as it goes through that bottom point, okay, it starts slowing back down because it's going back up in the gravitational field. Okay? So the energy is being converted back into gravitational potential energy. So in this example, we have two forms of energy. We've got gravitational potential energy because I've lifted it up, and we've got the kinetic energy of motion. And the energy in this system is conserved. It's just being constantly traded back and forth between the gravitational potential energy and the kinetic energy. So when we're saying that the energy is conserved, we don't mean that it's always conserved as kinetic energy, or it's always conserved as gravitational energy, or thermal energy, but the total amount of it combined is a constant for this system. Okay? And I, as a physicist, am so sure that this is actually conserved, okay, that I believe with 100% confidence that this bowling ball, if I give it initial gravitational potential energy, cannot come back with more gravitational potential energy than I initially gave it. Okay? There is no other forces acting on it, okay, other than me and gravity. We know the effect of gravity. It comes to the gravitational potential energy. Okay? So I'm going to be very trusting of nature. And I'm going to hold this bowling ball, which is incredibly heavy, right against my nose. I'm going to let it go. And please, Newton, be right. Okay, I have no fear that that ball was going to come back any higher than it originally did. Oh, I did that, unless I walk into it like that. Okay, let's look at a fun example of conservation of energy. This exact same problem, but on a more thrilling scale, which is a roller coaster, right? So roller coasters, how do they work? You usually have a roller coaster car that is lifted usually by a chain up to the top of a high hill. And what they're doing when they're lifting the car up is basically giving it an initial gravitational potential energy. And after that point, it's just you and Newton, okay? The constant transfer of gravitational potential energy to kinetic energy and then back to gravitational potential energy. Okay? So we've got initial gravitational potential energy as the roller coaster comes down. It's picking up kinetic energy. Okay? So you're trading the thrill of being in a high place to a thrill of moving really fast as you're transferring the gravitational potential energy to kinetic energy. And then back as you're going up the loop, right? You're changing that kinetic energy back to potential energy as you're going up, okay? And then so forth on the roller coaster. So roller coasters really act just by giving you initial potential energy and then letting it move forward. By the way, it's possible to design really bad roller coasters, like this, which we'll talk about a little bit next week, which doesn't make the loop-to-loop. Okay? So we'll talk a little bit about how to make good roller coasters and bad roller coasters. But let's come back to the question that was asked earlier over here about the work that we're doing in this case. Okay? So when we talked about lifting the block up, right, we know that we have to, for lifting it straight up, we have to counter the weight, and we're lifting it over a distance, right? And the amount of work we do in this case is, let's see, do I want to, let me, even though I saved that, let's put that up here and let me redraw it just underneath. We want to lift that block up onto that table. We can do what we already did, which is just lift it directly upwards. In which case, we've got, remember the work we do. Is force times distance. Okay? So we claim that if we lift that block up on the table, okay, and set it up there, we've done a certain amount of work on it. The work is equal to the weight of the block times the height. Okay? It's a heavy object. That weight can be a pretty strong force. Okay? But there are other ways to get that block up onto that table. And the other way that we've seen is that we could use a ramp, right? So in terms of the ramp, remember when we're pushing that object up the ramp, we have to provide a force on it. And that force is much less than the weight. That just means much less than. Let me just put it as less than. So we provide a force which is small compared to the full weight of the object. Right? So you might think, well, maybe we're not doing the same amount of work to get it up there. But the distance, the length of the ramp, is much larger than the height, at least for a highly inclined plane. Okay? So the work we do to get that block up there is equal to the force times the distance, but there are many different ways of doing that. Okay? In this case, we're doing the sort of the maximum amount of force over the smallest distance. And in this case, we're doing a much smaller force, but over a much longer distance going up the ramp. Okay? And so the amount of work that they do is the same in both cases. So the amount of energy we are putting into that block by setting it on the table doesn't change, okay, depending on how we get it up there. We can get it up there either with a big force acting over a small distance or a small force acting over a big distance. Okay? That block is up there on the top. It is the same amount of energy that we have transferred to it in both cases. Okay, let me show you another example. This is just, so that is mechanical advantage. Again, okay, so just in terms of energy instead of forces. Okay? So in terms of forces, we know to get that block up the ramp, we can apply a much smaller force than the weight to push it up. In terms of energy, we know that we can do a much smaller force over a longer distance and do the same amount of work. Okay? That is the exact same way that pulleys work, or block and tackle. So this is a pulley, so we just have a rope that is running over multiple pulleys here in this little sling. And I am incredibly strong, but I'm not that strong. Okay, I'm going to sit in this chair and get down on the ground. Let's see, yep, I'm up there on the screen. I don't want them to miss this. Okay, so, hey, I'm down on the ground. I'm going to lift myself up. If I were just trying to lift myself up, I would just have to apply a force in the vertical direction. That force would be about 150 pounds to lift myself up. Yeah, I wish. But that's that's a lot of weight to lift. Okay, so if I want to lift myself up the same distance, I can apply a smaller force as long as it's acting over a much longer distance, and pulley is a way to do that. Okay, so I'm going to be applying a force on this rope, but the amount of rope, let's see how much I lift here as I'm pulling. Okay, so I'm pulling up. You can see I'm using a lot of rope, right? The force that I am that I'm putting on the system is acting over a very long distance. It's the amount of rope that I'm wrapping around my hands here. You can see I'm not raising myself very far. Okay? All I'm doing in this case is doing the same amount of work it would take to lift myself up, but I'm doing it by a little force acting over a very long distance. It's hard to do this and talk at the same time. Okay, so you can see that this is another form of mechanical advantage. This is basically the same thing as a ramp. Okay? It's just doing it with ropes instead of the inclined plane. Okay? But it's the same idea, a small force acting over a long distance to lift a heavy object. That's a little rude, isn't it? A heavy object, a fixed distance. So, thanks. Okay, I'm gonna let myself down. So next week we're gonna start talking about rotation, which gets really interesting. So.